Hi everyone. So we're going to do one more example on that plane intersection, and then we're going to start the new section on polar coordinates and coordinate systems. Okay, so lines of intersection. Okay, so let's say we have two planes. So I'll say plane number one is given by x plus 2y minus z is equal to 5. And plane number two, that's given by x minus 4y plus z is equal to 3. Now, we know that the orientation of a plane, so how it's set up in 3D space, is given by the normal. And the normal is provided by these coefficients. So there, and there, and then here, here, and here. So we can write these two normals as n1. That's going to be 1, 2, minus 1. And n2, that's going to be 1, minus 4, and 1. Okay, so we can use the two normals to compare the planes to see how they're orientated with respect to each other. So note that n1 is not equal to some multiple of n2. Okay, so they're not parallel to each other because one is not a multiple of the other. So they are not parallel. Okay, so remember what parallel means. Okay, so parallel means if we have one plane on the top, one plane at the bottom, they are in line with each other, and so there's no intersection. It's the same as if you had parallel lines, they wouldn't intersect. So in terms of normals, we have this normal sticking up 90 degrees to the surface. The second plane, we have another normal sticking up, and we can see that they are in line with each other. Okay, so that means they're parallel here. So these are, the normals are in line, which means the planes are in line with each other as well. Okay, so that's parallel. Just for completeness, let's do perpendicular as well, or orthogonal. Orthogonal. Okay, so that's another case that we can have. That's when one plane looks like this, and another plane cuts it like that. So here we have this normal going this way, and here we have this normal going this way. And we see if we just move those vectors around just to the side here, we've got this one going that way, the blue one going up like that. We see that these are perpendicular to each other. Okay, 90 degrees, which means the planes are also 90 degrees to each other. Okay, and we know how to check for if two vectors are perpendicular. If n1 dot product with n2, if this is equal to 0, then we know that they are perpendicular, and so the planes are also perpendicular. Okay, so that's the two cases there, parallel and orthogonal. And if it's not parallel and it's not orthogonal, then we have another picture like this. Okay, where it's at some other angle to each other. Something like that, some different angle theta. Okay, so that's like the general case if they're not parallel. They're at some angle theta to each other, and then a special case of that is if that angle is 90, then they are orthogonal to each other. Yeah, so that's the different pictures that you should keep in mind when you're thinking about the orientation of planes. Okay, let's get back to this problem though. So we've got plane number one given by this, plane number two given by that. We've already noted that they're not parallel. which means there's some intersection line between them. So they intersect each other along some line. Okay, so our goal is now to find this line where they intersect. Okay, the intersection line. So what we want to do is find all the points that lie on plane number 1 and that lie on plane number 2. Okay, because if they lie on both the planes, then they must be a part of this intersection line between them. Okay, same if they're orthogonal. Okay, we've got this intersection line here. Okay, so we want to find all x, y, z that are on plane number 1 and plane number 2. Okay, so how do we do that? Well, if it needs to be on the first plane and the second plane, that's equivalent to solving the system of equations. Okay, because it must satisfy both equations for the point to be on both planes. So we've got the following system. X plus 2y minus z is equal to 5. X minus 4y plus z is equal to 3. Okay, so we take the two plane equations and we treat them as linear equations like we did at the beginning of the semester. Okay, and we try and find a solution or multiple solutions. Okay, so we can't find an inverse for this because there's 2 equations and 3 unknowns. To do the inverse method, we need 3 equations, 3 unknowns, and the coefficient matrix needs to be invertible. Okay, so we can't do that here. So we go back to the old method of augmented matrices. So let's write that out. So we have 1, 2, minus 1, 1, minus 4, and 1. Vertical line, 5, 3. Okay, and then we just treat it as a normal augmented matrix. So we've got 1 in the first row, first column, 1 in the second row, first column. We need that to be a 0. Okay, so let's take row 2 minus row 1. Okay, so that's going to give us 1, 2, minus 1, 5. 1 minus 1, that's 0. Minus 4 minus 2, that's minus 6. 1 minus minus 1, that's 1 plus 1, that's going to be 2. And 3 minus 5, that's minus 2. Okay. Now we need this element here, this minus 6. We need that to be a 1. And the 2 up here, we need that to be a 0. Okay, so looking at the second one, we can divide through by minus 6. That will turn that into a 1. So row 2, divide by minus 6. So we're going to have 1, 2, minus 1, 5, 0, 1, minus 2 over 6. We can write that as minus 1 over 3. Minus 2 over minus 6, we can just write that as 1 over 3. Okay, good. Now we still need this top element here to be a 0. So we're going to take row 1 minus 2 row 2. Okay, so we're going to get 1, 0. And then here we're going to get minus 1. Minus 2 times minus a third. So that's going to be minus 1 plus 2/3. And then 5 minus 2/3. Okay, and then we have 0, 1, minus a third, 1/3. Okay, so let's just work out what those two sums are. So we're going to get 1, 0, minus 1 plus 2/3. It's going to be minus a third. And 5 minus 2/3, that's the same thing as, if we just do it on the side here, 15 over 3 minus 2/3. So that's going to be 13 over 3. Okay, and then the second row stays the same, 0, 1 minus 1/3, 1/3. Okay, good. So we can leave it at this because we've got the 1, 0 in the first column, 0, 1 in the second column. We can't do anything more than that. So let's rewrite this back as a system so we can see what X, Y, and Z should be. Okay, and for completeness, let's just put the 0, 0, 0, 0. Okay, you don't need to do this, but maybe it helps you to see this better. So we're going to have X minus 1/3 Z is equal to 13 over 3. Y minus 1/3 Z is equal to 1/3. And the last one, remember, that's if you have a dependent row. So for that, Z can be anything. So let's just say Z is equal to T, which is some real number. Okay, so this T is going to play the role of that parameter in the line equation. Okay, remember, we got the R0 plus T times V. That's going to play the role there. Okay, so let's solve for X, Y, and Z. So X is going to be 13 over 3 plus 1/3 Z, but Z is going to be T. Y is going to be 1/3 plus 1/3 Z, but Z is T, and Z is just T. Okay, so putting this all together in a vector equation, we see that R of T is going to be equal to the constants that we had. So that's 13 over 3, 1 over 3, and 0. And then everything multiplied by T, we can put as a separate term. So that's T times 1/3, 1/3, and 1. Okay, and this gives us the line of intersection. Okay, so if your two planes are not parallel, then there's going to be some kind of intersection line that you can find. Okay, it's very similar to how if you have two lines in 2D, okay, so if you just draw two lines like this, if they're parallel, they're not going to intersect. However, if one is at some other angle to the other, like that, then there's going to be some intersection here. Okay, the same thing happens with planes in 3D. Okay, and then that's the vector form. So if I ask you what's the line of intersection, like by default, you can just leave it as the vector form. Or if I specify symmetric form, you know what to do, or parametric form, you know what to do. Okay, but if I don't specify, then the vector form is perfectly fine. Okay, so that's it for lines and planes. There's one more tutorial just going over distances between points, lines, and planes. That's going to be for next week. And then the tutorial after that is going to be on this new section that we're covering now, and that is polar coordinates. Okay, so let's start with that. Okay, so we'll start off generally with coordinate systems. Okay, so everyone should be familiar with Cartesian coordinates. There are actually many more coordinates that you can use. Okay, so let's just start off here. So let's say we have some kind of space. Okay, just being very general, doesn't matter what the space is. Okay, we've got a space of points, and we would like to label the points in the space. Okay, for some reason. Maybe we're trying to solve a physics problem and we need to label where the particles are, or something like that. We would just like to label these points. Okay, so the way that we label the points is by setting up a coordinate system. Okay, so what we can do is, let's say this is like a field, okay, or just somewhere on the ground. You can stand here, let's say at this point, and we say that is our origin. Okay, origin O. Okay, you can pick the origin wherever you like, but this is just to give you a mental picture of what we're trying to do. Okay, so we pick a point, we call that the origin O. And if this is 2D, then we need to pick 2 directions. Okay, so 2 dimensions, 2 directions. So let's say over here, east to west, we've got a line along this direction here. We call that X. And then we have another line going this way. We call that Y. Yeah, and we make sure that these 2 lines are perpendicular. So we'll see that they don't actually need to be perpendicular. But in this case, if we choose them to be perpendicular, you'll see we're building up the Cartesian coordinate system. Okay, now along the horizontal direction, we're going to make equidistant vertical lines. For example, every step we could put a vertical line, or every meter, something like that. We've got some units of equidistance. Okay, so we do that. So in equidistant intervals, we set up vertical lines. Like that, and behind us as well. Okay, those are supposed to be equidistant. Okay, and then going vertically, we draw ourselves horizontal lines, again, equidistant. Now, the vertical distance here, this distance, the vertical distance there, and this horizontal distance here, they don't need to be the same. Okay, there's no rule saying that they have to be the same, but if they are the same, then you know that we're dealing with Cartesian coordinates. Okay, so in this case, let's just say that they are the same. So we draw this, going along. Like that. So now we end up with a grid of points, because our vertical lines and horizontal lines, they're going to intersect each other at some points here. Okay, and that is what we use to label these points here. So from the origin, if we count 2 spaces to the right, or 2 lengths to the right, 1 unit up, we call this point 2, 1. Okay, that's the label that we give to that point. It's the distance we moved horizontally, the distance we moved vertically. Those 2 numbers, we call that the coordinates, and that labels the point. Okay, so this is a Cartesian kind of system, but we don't need to use Cartesian. We could use something else. So let's do something a bit different and say that these spacings are different for vertical and horizontal. Okay, so let's call this system A. And we have system B. We've got exactly the same field. Say like that. Let's say we pick the same origin O. Okay, but now the horizontal spacing and the vertical spacing, I'm going to make that different. So let's say that the vertical spacing is like this. So we can call that 1. Okay, so it's 1 unit spaced vertical lines. Okay, however, going horizontally, so with the vertical lines, I'm going to make it 2 units. So like, sorry, let's get that straight, like there. Okay, so you see this is no longer Cartesian coordinates, because the horizontal spacing and the vertical spacing are now different. Now, if we look at this point, 2, 1, in our first system A, it's given by 2, 1. In our second system, it's not going to be 2, 1 anymore, because the horizontal spacing is now doubled. So in fact, the same point, it's over here. This is going to be 1, 1. Okay, because before we went across 2, so we counted 2 spacings there, we went up 1 here, and we got the point 2, 1. In this picture, 1 spacing horizontally is equivalent to 2 spacings in the previous system. Okay, and then we go up here. So this point is actually 1, 1 now. Okay, because the horizontal distance, let's say delta x in the A system, in the B system, delta x B is twice delta x A. Okay, so before it was 2 spacings, here it only took us 1 spacing to get there. Okay, and the vertical is the same. So in the vertical spacing was 1 before, it's still 1, so the y coordinates is the same. But the idea is that in the A system, the label was 2, 1. In the B system, the label is 1, 1. It's different labels, but it's exactly the same points. Okay, so the idea. We can have different coordinate systems labeling the same points. Okay, so you've got the same points in both cases, but a different label because you're using a different coordinate system. Okay, so the coordinate system has nothing to do with the points. The points remain the same. However, the labels are now different. Okay, so you should just keep that in mind. So let's look at something a bit more different than this. So let's say we have system C. Again, same sort of field. Again, let's pick the same origin just to keep things a bit simpler. But of course, you're free to move the origin to wherever you like. Now I'm going to do something a bit more crazy. The horizontal lines are going to stay the same. So we've got like that. Okay, so I've increased the spacing between the horizontal lines here, going vertically. Okay, and then for the other lines, I'm not going to draw vertical lines. I'm going to draw angled lines, something like this. Okay, so now the angle between them has changed, this angle theta. So before the angle was 90 for system B and system A, but now it's a different angle. And of course, we could still label the points. There's no problem with that. If we wanted to label this point over here, how would we do that? Well, how do we get to that point? We need to walk across 1 unit to get to this line, and then we walk up this amount here. And that labels the point as 1, 2. Okay, so you can have slanted lines, no problem. The labeling system just changes, but the points are the same. Yeah, so we've got something like that. Okay, so this is not Cartesian anymore. This is some other system. Maybe it's got a name. Okay, but again, in this case, you can easily find what the labels are. Okay, just by moving across and then moving along, that will give you your label. Okay, so far we've been dealing with lines. So orthogonal lines with different spacings, slanted lines with different spacings. But again, like I said, coordinate systems can be quite crazy. We don't even have to use lines. We can use some other kind of curve. Okay, so let's look at this type of coordinate system, system D. Again, we've got an origin. Let's say we're standing here. But now I'm not going to draw slanted lines or vertical lines or horizontal lines. I'm going to draw, first of all, radial lines. So from where I'm standing, I'm going to draw lines going out in all directions. So line going up here, going out there, out there, out there, like so. Okay, but imagine like infinitely many lines, but I'm just drawing a few to get the idea across. So all going all out in different directions, we call these the radial lines. Okay, like that. So that's my one set of lines, but remember this is two-dimensional, so I need another set of lines. Like we have here, we've got the green and the red. I've drawn in green, now I need to draw in the red. Okay, now again, I'm not going to draw vertical or horizontal lines. Now I'm going to draw circles. Okay, so I've drawn circles going out like this. Okay, so I've got two lines, they cover the space, and the intersections, they give me the points that I can label. So how do I label these points now? So let's say I want to label this point. Okay, just like I labeled these other points. So this one was 1, 2, and so on. Okay, so how do I label that? Well, I pick one of these radial lines to be a special radial line. Okay, so let's just pick this one. So this is my special line here. What I do is I measure the angle that this point makes with this special line here. So let's put that in yellow. So I've got that line from me to the point. This angle is theta. That's going to be my first number that I have here. So theta. And then I need another number, just like here I have 1, 2. I've got two numbers for two dimensions. I need two numbers here. This distance, I'm going to call r for radial, like radial distance. So I've got these two numbers, r and theta. And those are what I use to label the points, r and theta. Okay, so this gives us a labeling for all the points. So if you imagine some points over here, let's put that in blue. Same sort of thing. We measure the distance from where you're standing to the point. That's going to be r. The angle to that special line that I mentioned here, that's going to be theta. So this point is given by r and theta, but now the blue version. Okay, so radial distance r, that's my first number. Angle to the special line, I call that theta, and then the point is r and theta. Okay, so this is called polar coordinates. Okay, so the first one we went through, that was Cartesian coordinates. So vertical lines, horizontal lines at 90 degrees with equal spacing, that's Cartesian. Okay, and then we've got these other ones that we invented. And then this last one, it's got a name for itself. Those are polar coordinates. So from where the origin is, we draw out radial lines. We draw circles at the different radii. And then we use the distance to the point and the angle it makes with the special line. And then that gives us the labeling for that point. Okay, so that's called polar coordinates. Okay, so note. Since the points in the space are not affected by the choice of coordinate system, okay, so remember, you can pick whichever coordinate system you like. It doesn't change the points in the space. They don't care what coordinate system you choose. There should be a way to convert from one coordinate system to another. Okay, so what do I mean by that? Well, if I'm picking polar coordinates and I give you a point and I say, let's say this is point P. If I say point P is at the point r theta with my polar coordinates, and you're standing there and you say, no, I don't want to use polar coordinates. I want to use Cartesian coordinates. And you give me a different label for point P. Okay, we're both labeling the same point, but the labeling is going to be different. But since it is the same point, there should be a way to get from one label to the other label. And we call that a coordinate transformation. Okay, so we're going to find a coordinate transformation from the original Cartesian coordinates that we looked at to this new polar coordinates that we've been looking at. Okay, so the way that we do that is we set up the Cartesian coordinate system. So let's say that's the one that you're using. So we've got X and we've got Y and we've got point P. Okay, that's going to be our reference point that we're going to use to go between the systems. And as always, we've got our origin here. Okay, so in Cartesian coordinates, how would you label this point? Okay, so what did I use here? I used green for the horizontal lines, so let's stick with that. So we've got this green line going along there, red line going along there. So we would say that is X, this is Y, and so P is given by XY in Cartesian coordinates. So P is given by X, Y in Cartesian coordinates, but we could do exactly the same in polar coordinates. So what would the polar coordinate form be? Let's use some different colors now. So let's say gray. Remember, we need to find the distance r. Okay, that's part of the polar coordinates thing. And then let's use black here for this angle theta. Okay, so this is Cartesian. And we can do the same thing with polar. So P is then given by r comma theta for polar. Okay, so how do we go from one to the other? Well, look at what we've set up here. We've set up ourselves a right angled triangle with a radius or hypotenuse r and angle theta. The opposite is given by y, the adjacent is given by x. So we can just use a bit of trig to go back and forth. Okay, so let's say we're given x and y. How do we find r and theta? So given xy, how do we find r theta? Okay, but r is just the hypotenuse. So r is equal to the square root of x squared plus y squared. So if I give you xy, you can find r using the distance formula. So square root of x squared plus y squared. What about theta? Well, the opposite is y, the adjacent is x, so tan theta is y over x. So theta is going to be arctan of y over x. Okay, so that's how we find r and theta given x and y. What about the other way around? Because remember, we should go back and forth. So that's number one. Number two, given r theta, how do we find xy? Okay, and I'm sure you already see the answer here. If I want to find x and I'm given r and theta, x is just going to be r cos theta. And y, I'm sure you know that already now. Y is the opposite here. So r sin theta will give us y. Okay, so we've written out the coordinate transformations. If I want to go from Cartesian to polar, I use this first one. So this is given Cartesian, how do we get polar? We can use this first way. Or if I'm given the polar coordinates, how do I find the Cartesian? Well, I can do it the second way. Okay. So I can use either of these methods to go back and forth between Cartesian and polar coordinates. Okay, any questions so far? Okay, so let's put up some homework problems for you to try this going back and forth here. So homework problems. Okay, so we have 1, 2, 3, 1, 2, 3. Okay, so for the first part of the homework problem, please convert these Cartesian coordinates to polar coordinates. So I've got 0, -1, 3, 2, and -2, 5. Okay, so those are in Cartesian. Please convert them to polar. And then in the other case, I'm going to give you polar. Please provide the Cartesian. So this is going to be 2 pi over 3, 1 and pi over 2, and 5 and pi over 4. Okay, so just a note with the polar. Remember, r is a radial distance. So since it's a distance, this first part must always be positive. So that's always a check that you need to make. Must be positive because r is greater than or equal to 0. Right? You can have a distance of 0. That just means you're at the origin, but you can't have a negative distance. So whenever you're working with polar and Cartesian, x and y, they can be positive and negative, no problems there. In polar, the radial distance has to be positive. Okay, so we see that here. So this is the r component, that's always positive. Okay, so 6 homework problems there. Any questions on these? Okay, so not too bad. And then just a little note for next lecture. Okay, so converting graphs from Cartesian to polar. And from polar to Cartesian. Okay, because we know how to go back and forth now. Okay, just as an example, if I have a graph in Cartesian form, let's say y equals 1 over x. Okay, so I'm using my xy variables for Cartesian graph. how does this change to a polar graph? Okay, what does that look like? Okay, so the graph is going to look exactly the same, but now it's going to be in a different coordinate system. Okay, and then we'll also see how we go back. Okay, so if I give you a graph in polar coordinates, something like r as a function of theta, for example, how can I go back to a Cartesian? Okay, we're going to have a look at that in the next lecture. Okay, any questions on what we've covered today? Okay, cool. If you do have any questions later, please just send me an email or ask on the WhatsApp group. The tutors are there as well to answer questions. And then later on today, I will post the solutions to the homework problems here. So then you can just check your answers. Okay, and then we'll carry on with this tomorrow. Okay, bye everyone.